Okay, good morning or afternoon, Algebra 2 students. This is Mr. Bear, and I am bringing to you the lesson 13.2, Intro to Logarithms, okay? Hopefully by now you have done the bell work and your teacher has gone over these, but if not, or if you need more clarity on these, here are the answers you should have had. First of all, we can scratch off number 1, part A. That was a goof up. I did not mean to put that problem. Part B, probability of other or female. Probability of other is 23 out of 60, plus the probability of female, which is 28 out of 60, minus the overlap, the ones that are females and other. So that's going to be minus 13 out of 60. Okay, so that should give you, let's see if we do the math on this. It looks like 38 out of 60. Female given rugby, so we're only looking at those who play rugby. So the females who play rugby is 8 out of 20. And for the football given female, so for football given female, we are only looking at the females, so 7 out of 28. Oops, 7 out of 28. There we go. There's our answers to that one. On the second one, we're going to rewrite this as 4 over 15x times 5x over 4. Those 4's will cancel, and the x's will cancel, so we get 5/15, which simplifies to a third. For the next one, I'm going to rewrite this as a multiplication problem. So we're going to have x minus 4 over x squared minus 9 times, I'm going to flip-flop the bottom fraction. Then I'm going to factor everything that can factor. So x squared minus 9 is x plus 3 and x minus 3. I'm going to use the ACB tree on the numerator of the second fraction. So what multiplies to 9 and adds to 6? Well, that's x plus 3 and x plus 3. And then x squared minus 16 is x plus 4 and x minus 4. So then we do our canceling. So I can cancel out an x minus 4 and an x minus 3 and an x plus 3. So all that's left is 1 over x plus 4. Okay. All right, next problem. F of x plus g of x. So f of x is 3x minus 1. G of x is 2x. Combine your like terms, you get 5x minus 1. G of f of x means we're going to take our g function, which is 2x, and we're going to replace the x in that function with the f of x function, which is 3x minus 1. Distribute that, and you get 6x minus 2. For the next one, we figure out g of 2 first. So we use our g of x function, plug in 2, and we get 4. Then we use that 4 to evaluate in the f function, which is 3 times 4 minus 1, which gives you 11. For the last one, to write this exponential function, we first need our a value, which is the y-intercept. Look where x is 0, your a value is 2. Now for our b value, we look to see how the outputs change as we go along. Looks like we multiply by 4 each time, so your b is 4. So your answer is y equals 2 times 4 to the x. All right, so let's get into today's lesson. So reminder about last time, the definition of an inverse is when you switch the inputs, which is the x's, and the outputs, which is the y. So we're going to look at this function y equals 2 to the x. So you can see we've got the equation. This is exponential, by the way. We have our table of values, so what we would get when we plug in different x values to that function. And our graph looks like the graph that we see here. I'm going to make note of some points that are on this graph. There we go. All right, for the inverse, if we were to switch the x and y around, we'd have x equals 2 to the y. But then the question becomes, what in the world does this look like when I try to solve for y? I can't just divide by 2 because this is not 2 times y, it's 2 to the power of y. But what I can do is I can make a new table where I flip-flop the x and y's. Okay, so that's what we're going to do first. So I'm going to make my old y values my x values. I'm going to make my old x values my y values. And we're going to go ahead and graph this. So 1/4 -2 will be about right there. 1/2 -1 will probably be about right there. Then we have 1, 0, 2, 1, 4, 2, and then we'll have 8, 3. And we're going to notice a graph that kind of looks like this. Okay? All right, so now what in the world would we call this function? Okay, well, we have to give this a name. So the name for this inverse function that we just graphed is called a logarithmic. So it's a logarithm function. When we write the inverse of this as x equals 2y, it's not helpful because y is not isolated. To write it as an equation with y isolated, we have something called log form that allows us to rewrite exponential equations. So if you have an equation like y equals 2 to the x, when we do our inverse, you end up with x equals 2 to the y. So what we're going to do is we're going to write this in log form. So what we're going to do is we're going to take the logarithm of both sides of our equation, okay? And so whatever the base of your exponential is becomes the base of your logarithm, okay? And this can be generalized for any base. So y equals a to the x. We write this inverse as log base a. Okay, so if you look here at the bottom of this page, you'll see y equals a to the x converts into x equals log base a of y. Okay, so we're going to practice doing some converting. So for part 1, we're going to convert each of these exponentials into their logarithmic form. So I'm going to be looking at this particular transformation, if you will, right here, the ones in colors. So when I write part A, first thing I notice is I have a base of 5. So I'm going to write log base 5 of the 625. And logarithms are always equal to whatever the exponent is. So whatever your exponent is in the exponential becomes what your logarithm is equal to. So if I look at this next one, so it'll be log base 4 of 1/64 equals my exponent of -3. For the next one, we have log base 81 of 9 equals our exponent of 1/2. And generally, on this last one, we have log base x of z is equal to our exponent, which is y. Okay? Now, we can also go the other way. We can go from a log form to an exponential. So to do that, we first identify the base of the log. So the base of this log is 2. Since the log is equal to 5, that becomes the exponent on the base. So 2 to the 5th equals 32. On the next one, the base of the log is 4. The logarithm is equal to 1/2, so that's the exponent. And 4 to the 1/2 is 2. Next one, we have 2 to the -4 equals 1/16. And generally, the last one, we have x to the power of z equals y. Okay? Now, try these ones on your own real quick. Convert them to exponential form. You could pause the video and try these out. Okay, if you did this right, you had 2 to the -3 equals 1/8. 5 squared equals 25. 20 squared equals 400, and 17 squared equals 289. Now try these. These ask you to write into logarithmic form. So pause the video, try this out. If you did this right, you had log base 4 of 2 is equal to 1/2. For 22, you have log base 3 of 243 equals 5. For 23, you have log base 14 of 1 over 196 equals -2. And finally, we have log base 18 of 324 equals 2. Okay, now that we know how to convert between these forms, let's evaluate some logarithms. So part 2 is all about trying to figure out what the value of the logarithm is. So understanding that logs are inverses of exponentials might be helpful first to rewrite these as exponential. So you'll probably see the problem say, what is log base 3 of 27? I always make that set equal to x so that I can write my exponential. So 3 to the x equals 27. Well, ask yourself, 3 to what power gives you 27? And the answer would be 3. So log base 3 of 27 equals 3 because 3 to the third power equals 27. For the next one, you'd write 5 to the x equals 25. And then you want to ask yourself, 5 to what power gives me 25? Well, if I do 5 squared, that's 25. So that means x equals 2. And therefore, the log of base 5 of 25 is equal to 2. On the next one, we're asking ourselves, 1/2 to what exponent gives me 1/8? Well, when I look at a problem like this, I ask myself, okay, well, what can I what power do I use for 1 to make 1? Well, I can use any power for that. So let's try the 2. So 2 to what power gives me 8? Well, I know 2 to the third is 8. 1 to the third is just 1. So it turns out that x equals 3 because 1/2 to the power of 3 gives you 1/8. 1/2 times 1/2 times 1/2 is 1/8. Okay? Next one, we have 1/3 to what power gives you 9? Well, we may remember that if we were to write this we know that 3 squared will equal 9, but how do I make a reciprocal of that 3 to make it 1/3? Well, I can do that if I make this as 3 to the -2, that would give me 1/9. So if I have 1/3 to the -2, I would get 9. So x equals -2 here. When you have a negative exponent, you just do the reciprocal of your base and then have the positive exponent. The next two logs are special logs. Well, not really special, but they're properties of logs that we'll get used to. So log base 6 of 6. Notice the base and this thing are the same. So we ask ourselves, 6 to what power equals 6? Well, that would just be 1. So when your base and the logarithm is the same, when these are the same, your answer is always going to be 1. Now the next one, if I look at this one, we have 8 to what power gives you 1? Well, anything raised to the power of 0 equals 1. So if you have a logarithm where 1 is the argument, by the way, this thing is called an argument, the answer will always be 0. So x equals 0 here. Okay? All right, last two. 2/3 to the x equals 8 over 27. So this one's similar to example 5 in that we would first look at, 2/3 times 2/3. That gives me 4/9. If I multiply by another 2/3, that'll give me 8 over 27. So my exponent has to be 3 because I multiplied 2/3 times itself 3 times to get 8/27. All right, last one here. So 4 to the x equals -16. Well, let's see what happens here. If I think about a function y equals 4 to the x, if I made a table of values for this, if I did, let's say, let me think of this a different way. All right, let's look at a pattern here. If I have 4 squared, I get 16. 4 to the first gives me 4. 4 to the 0 equals 1. Then if I were to continue that trend, 4 to the negative 1 would be 1/4. 4 to the negative 2 would be 1 over 4 squared, which is 16. 4 to the negative 3 would be 1 over 4 cubed, which is 64. If you notice here, even with negative exponents, our fractions are not going below 0. Okay, so it turns out we're never going to be able to have a value for a logarithm that will be negative. So in a problem like this, x is no solution. Okay, so the way you're going to remember this is you cannot have negative logs. Okay, just like at school, we don't want negative logs. So in logarithms, we want no negative logs. Okay? All right, pause your video, try these out, see if you can evaluate these. Okay, now that you've done that, let's see what you got. So on this one, we should have had 4. For this one, we should have had negative 1/2. Oh, we shouldn't have. Or yeah, we should have. Sorry. For this one, you should have 2. And for this one, you'd have negative 2. I'm going to go back over B real quick. So 4 to what power equals 1/2? Well, I know that the square root of 4 is equal to 2, which means 4 to the 1/2 equals 2. But to make it a reciprocal or a fraction, we have to make a negative exponent. Okay? So that's why x is negative 1/2 there. All right, we have a couple of special case logs that we need to talk about. I'll just do these really quickly. One is called a natural log, which we use LN for the abbreviation. Okay, it's Euler's number, and it's a famous irrational number, and we use the letter E for that, which is about 2.716. The LN button on your calculator will allow you to calculate logs with this base, and it has the same properties as any other logs. Okay, and we'll talk more about those in the next lesson. Okay, so what you need to know is that log base E is the same as saying natural log. The relationship between E and natural log is that they cancel each other out. So if I have E to the natural log of 5, the E cancels with the natural log, and I just have 5. If I have natural log of E to the x plus 1, I would cancel the natural log in E and just get x plus 1. Another example of a special log is the common log. Every log needs to have a base. So if a base is not written, we're going to assume the base to be 10. Okay, so what we're saying is if you see the log button on your calculator, so the log button is on your calculator, has a base of 10. So when you see log base 10 on your calculator, it's just going to be the log button. Okay, it will not have a number with it. It's just understood to be a 10. The relationship between log and 10 is they cancel each other out. So 10 to the log 4 is just 4, and log 10 squared is just 2. So with that, let's talk about how to calculate using these. All right, so on your calculator, the only bases that we can have are base 10 and base E. Those are the only calculator buttons that we have on our calculator with regards to logs. Okay, so if I do log 3 on my calculator, I'm going to type log 3, and I get 0.4771. If I do the natural log of 3, I get 1.0986. So that's how you would use the log button on your calculator. So let's practice rewriting in logarithmic form for each of these. So e to the 2x equals 4. So I see e. So instead of writing log base e, of 4 equals 2x, instead of writing log base e, we're going to instead write ln 4 equals 2x. Okay? So then on the next one, instead of log base e of 12, we're going to write natural log of 12 equals x plus 7. For these base 10s, instead of writing log base 10 of 50 equals 3x, so instead of this part, we're just going to write this as log 50 equals 3x. And the next one would be log 350 equals 2x minus 7. Okay. And then finally, we should be able to do this in reverse. So here we have log forms, we're going to write exponential. Here I see natural log, so that means base of e, power will be 5, e to the 5th equals x minus 4. Next one is as the common log, so we'll write that as base 10 to the exponent 5x equals x plus 7. Next one is also a log without a base, so it's base 10. 10 to the negative 2 equals 9x minus 8. And then finally, the last one, natural log, means base e, so e to the 3x equals 5x minus 3. All right, I know that was a lot for a video, but we have come to the end, so now you're going to do your skill check and then complete your Unit 13.2 IP.